gonna talk about my interpretation that the language network doesn't exist. And I hope that by the end of today I convinced you about that. But I'm going to take you through a couple of examples, both in the healthy brain and in clinical cohorts, to show you why I came to this radical statement that some might consider very controversial at this point. You already heard about our YouTube channel. It's called Clinical Neuroanatomy Seminars. It's packed with talks, presentations, conference pitches. We do have a journal club every Monday morning, 9:30. Everyone is welcome. You're very welcome to join us live on Zoom, but you're also welcome to hide anonymously on YouTube and just watch it. But it's usually more fun when you're actually with us in the room. Right, so let's get started. I heard we have a mixed group this year, so not just medical students. What else do we have? Psychology? Oh, that's a lot less than I thought. Biology? Neurobiology? I'd take that one, yeah. What else? Everyone else is medic? Medicine? Yes! Have nothing to teach you. You know everything I know. Anything else? Okay, that's quite a range. So let's make sure we're all on the same page before we get started. The images that I'm showing you here is probably nothing new to you visually, but the concept that I want to reiterate is that there's not just one type of anatomy, but different types of anatomy, which may sound confusing to begin with, but we have what is known as surface anatomy, where you look at the gyri and the sulci of the brain, so the surface. We have sectional anatomy, where you slice through the brain. You can look at subcortical structures, you can look at the white and the grey differentiation, and the deep brain nuclei. We have connectional anatomy, so that's looking at the white matter connections that connect the different parts of the cortex, so the surface of the brain and the nuclei within the brain. And then we have functional anatomy, which is when someone goes in an MRI scanner, does some tasks, and you get the activation of the brain. Now, the reason I make this point is because when we talk about anatomy, there's many different terms that we can use, and they sometimes mean the same thing. So the example that I have for you here is in surface anatomy. We would call the gyrus before the central gyrus the precentral gyrus. The same part of the brain in sectional anatomy is called BA6. Does anyone know what BA stands for?
Brodmann area.
Brodmann area. What's Brodmann?
Person.
A person, correct. I was trying to trick you there. Yeah, he was a person who did cytoarchitecture stainings of the brain and divided up the brain into various different areas depending on when the cytoarchitecture of those areas changed. And we now just abbreviate it as BA Brodmann area. Then we have connectional anatomy, which is, in that particular instance, you would refer to the U-shaped fibers. And then in functional anatomy, the same part of the brain would be M1 or the motor cortex. Okay, so different types of anatomy come with their own nomenclature, but usually we often mean the same parts of the brain, just in different terms. It's one thing to bear in mind. The other thing is that I like to ask this question, which arguably isn't easy. Oh, I already see worried faces. It's arguably an easy question, but how many lobes does the brain have? And we just go by show of hands. Who thinks there's one lobe? You're allowed to ask your neighbor as well. 2, 3, 4, 5, okay, wow, okay. 6, 7. Some people miss an 8 on that slide. Anyone who is missing the 8? No. Okay, 5. Why 5? Can you name them? I love how the entire room went up. Yeah, 5. And now everyone's like, don't know which ones. Frontal, okay. Number 1. What else?
Parietal.
Parietal.
Temporal.
Occipital.
Temporal.
Temporal, yes. Occipital. Nah. That's, hang on, 4, right?
And then the limbic system.
Limbic system, 5. You said 6. Insular, that's right. So bottom line, you're all right. You're just stuck in different times of the development. So initially, when the first official nomenclature of anatomy came out, that was in 1895, they defined 4 lobes: the frontal, parietal, occipital, and temporal. Then in 1975, so this is living history now. I know a lot of people who were born around that time, so this is not old, right? We got 5 lobes, so they discovered the insula, which is when you pull apart the frontotemporal lobes. Inside of the brain, you have this little island that is known as the insular cortex. And then only in 96, so now you know people born around that time, the limbic lobe was discovered or described as a separate lobe of the brain. Now, I not only ask students that question, so I also ask the smartest things we have on this planet, apparently. So I asked Google, and in May this year, Google was convinced there is 4 lobes. When I asked Google again in September, it had new entries and it learned that in fact it is 6 lobes. Now Google is out now, we have ChatGPT, so I asked ChatGPT the same question, and here it depends how often you ask it. So the very first time I asked, it said 5 lobes, then I simply repeated the question and it said 4, and then I repeated the question again, it says 6. I also asked Bard, which is Google's AI client. Bard said 6 plus cerebellum. So it counted the 2 lobes of the cerebellum, so we had 8. That's why some people are also missing number 8 on the question slide. So the point here is, don't blindly rely on AI. It's not always smarter. And keep checking again if it changed its mind. So while Google became smarter and learned that it's actually 6 lobes, ChatGPT, at least the free version, became dumber. And it now continuously says it's 4 lobes, no matter how often you ask it. And I haven't tried the paid version, so don't know if that is smarter now. But careful with that. Now, if we do the same thing for the connections of the brain, you can talk to your neighbors again. How many connections, as in tracts, do you think the brain has? And we're going to go by show of hand again, starting with 10, 20, 30, 40, 50, well, one hand, 60, 70? Oh, wow. Why does everyone think it's 70? Who taught you that? Can you name them? No. The correct answer is we don't actually know, because, here we go, we're missing the gold standard. So no one really knows how many tracts there are in the brain. We can dissect out bundles, but individual tracts we don't really know just yet. Now, this beautiful image obviously shows all the connections in the brain. And for the sake of today, all you need to know about how we do that is the principle behind diffusion weighted imaging. And the principle is as follows. So you see this image. If I now ask you which way the road turns, who says left? Middle? Right? Okay, how do you make this judgment? There's a lot of discussion going on. It's not a trick question. What made you decide that the road is turning slightly to the right?
Because of the rear lights of the cars.
Right, what about them?
The left appeared to be reddish,
Mhm.
and the right ones appeared to be lighter, which means the front of the car.
Yeah,
And then it appears that the road bends to the right
what makes it appear like it?
because the road is not square in the picture.
But do you see the road?
No,
Aha. So how do you know the road is turning?
because of the lights.
Yeah, you're on the right track. By the way, the left and the right doesn't matter. This is a picture from the UK, so everything is the wrong way around. Oh, the relief. I was like, oh, that makes sense now. Okay, so you can't see the actual road, but you still all said slightly turning to the right, and you made a judgment based on the lights of the cars. But how? The lights per se don't tell you it's turning.
Because the lights are of the bars which are on the road.
Mm-hmm.
So it's the conclusion based on facts that we know.
Correct. And that's basically how diffusion imaging works. So we don't see the tracts, let alone the accents in the brain. What we see are the water molecules, and we assume if the water molecules are going that direction, then they can only go that direction if there is an infrastructure that supports their movement. So what you do is you take those individual lights, or in our case, the water molecules, and you piece them together. So you basically draw a line between them to indicate where the road is, in our case, the tracts. It's the fundamental principle of diffusion imaging, and that's all you got to know for today's purpose about how it works. And with that, we can then define the connections in the brain. Most of the connections that we know about these days were already described in the 19th century with postmortem blunt dissection. So this is taking a brain and carving out the connection anatomy inside the brain. Now, with the emergence of diffusion-weighted imaging, what we have added is color. And we can now dissect out slightly more connections because our resolution is getting better and better and better. Okay. Now, that's just to bring us all on the same page. Now we're changing gear towards the neurobiology of language. Okay. Now, when it comes to where language is in the brain, I'm sure you heard about. Wow, this really washed out. I'm sure you heard about Broca and Wernicke. Anyone? Yeah? Yeah? We're all good? Do you know anything about those two? Occupation, nationality, discoveries? Anything? Come on, you all heard about them. What they're famous for? Hmm?
Broca, he discovered like the motor cortex of speech
Mm-hmm.
from two people who had like, I don't know, tumors or strokes. And Wernicke, he discovered the part of the brain that he thought was made way for like the semantics of speech, language.
Very good, very good. So Paul Broca, French surgeon, discovered looking at stroke patients, that the inferior frontal gyrus is relevant for speech motor output. And Carl Wernicke described a part in the temporal lobe that he thought was important for understanding language. Now, the literature is full of papers that talk about Broca's area and Wernicke's area. In 2016, Tremblay and Dick actually went to the Society for the Neurobiology of Language. so arguably the experts in the field, and asked them where Broca and Wernicke are in the brain. And what you see here are the different possibilities they had to answer. So you can see area 44, 45. These numbers refer back to Brodmann areas. You can see area 44, 45, 47, only 44, or the ventral BA6, 44, 45, and a couple more possible distributions. But the compounding picture looks a bit like this, where the highest agreement for Broca's area was less than 50%. Far from ideal. Looking at Wernicke's area is even worse. It's less than 30%. So basically, even the experts don't really agree where these parts in the brain are. Now, here are the two. So we have Paul Broca on the left, we have Karl Wernicke in the middle, and then Norman Geschwind on the right. Anyone heard of Norman Geschwind? Some? Do you know anything about him? Fair enough. So Paul Broca, here you see one of the patients. You see the lesion in the inferior frontal gyrus. Does this thing have a pointer? Oh, it's very faint. So here is the inferior frontal gyrus, and there's a stroke lesion right here, causing that patient to not be able to articulate fluently anymore. Now, Karl Wernicke then reported a series of patients where he... Hi, coming in. Where he saw patients with a lesion in the posterior temporal gyrus, and these patients were completely fluent, but their comprehension of language was impaired, and so was the content of what they said. So they were fluent, but what they were saying made little to no sense. Now, what's interesting here is that we have the first model of language in the brain. And model in this case means areas that are connected with an idea of a mechanism behind it. And also we see the right side of the brain. Now, many, many years later, Norman Geschwind, an American neurologist, put the two together, and he said there's also a part of the brain that has to do with the integration and concepts, and he placed that in the angular gyrus, which is here, and the angular gyrus is part of the inferior parietal lobe. Now this now means that we have three areas for language processing in the brain, and they're connected. Does anyone know what the connection between them is called? That thing here. There's a lot of whispering. It's the arcuate fasciculus. Have you ever heard of it? That one. Okay. Now, if we put it all together, the neurobiology of language looks a bit like this. So we have three cortical areas in the frontal, the parietal, and the temporal lobe. And we have the arcuate fasciculus connecting the three. Initially described was only the red segment here, called the long segment, that connects the frontal and the temporal areas. And then in the early 2000s, Marco Catani also described this indirect connection here that relays in the inferior parietal lobe. So that's a classical anatomy of language. Now, let's look at some of the problems with that. So one of the most prominent models of language is the dorsal and ventral stream model of language, and I have two questions for you. First one is, what does dorsal and ventral mean? Anyone? Yep.
Dorsal is the top part of the brain,
Mm-hmm.
the downside of the brain.
Brilliant. Correct answer. So top or bottom or above and below is what these terms mean. Now the question is, what's the boundary between them? Where do we consider things as being dorsal and where do we consider things as being ventral? There's an anatomical structure that separates the two.
Lateral fissure.
The lateral fissure. So the lateral fissure is this part here that separates the frontal lobe, the parietal lobe, and the temporal lobe. So the idea is that everything that is above the lateral fissure is dorsal and everything that's below is ventral. Now, in terms of the neurobiology of language, that means that we have two streams and the white matter that was associated with them is for the dorsal, we have the frontoascending tract and the three segments of the arcuate fasciculus. For the ventral stream, we have the inferior fronto-occipital fasciculus here connecting the frontal and the occipital lobe. We have the uncinate that is called the hook. Uncinate just means hook, and it clips together the frontal lobe and the anterior temporal lobe. And then we have the inferior longitudinal fasciculus here that connects the anterior temporal lobe to the occipital lobe. So that's the anatomy of the dorsal network that you find in the literature. And here is one of the problems with that, and that is when you look at where these white matter connections terminate, they actually project above and below the lateral fissure that is right here. So that's for the dorsal network. For the ventral network, we have exactly the same. It connects above and below the lateral fissure. So separating the white matter into the dorsal and the ventral stream is not really helpful in this case. Now, coming back to our model of language in the brain. When we look at other models, they look like this. So for the visual system, each of these boxes is one part of the brain. Every line is a connection between them. Same for the auditory system. And we can see they're hugely complex models for functions that arguably are less complex than language. Yet, when you open most textbooks, the model for language that you see looks like this. So it's probably fair to say that this model of language is slightly oversimplified. Now, there are other models that have been proposed. Here's just a couple of them. You don't often find them in textbooks for various reasons, but let me just talk you through them very briefly. They come from different specialities. So on the top left, we have a model for psychiatry and autism. Then here we have the model that I just explained to you, the dorsal and the ventral stream model, that is actually based on evolutionary findings. So you probably heard about the where and the what pathways for the visual system. It's the same model applied to language in the brain. Then we have the London tube map from neurology, one of my favorites. But then my absolute favorite is this one from neurosurgery, where they completely forgot to put the brain, which is funny coming from a neurosurgeon. Now, the model of language in the brain has changed over time. The original 19th century model was those two cortical areas connected by one tract. Then in the early 2000s, we got the two other segments for the arcuate fasciculus that relay in the inferior parietal lobe. And since then, so really in the last 15 years roughly, all these connections have been added to the language network because they were identified in other modalities like direct cortical stimulation in neurosurgery or electrophysiological measures. So the network of language in the brain is continuously enlarging. Okay. Now, my favorite problem with the model. Any idea who these ladies are. Recognize any of them? If you get one, you get them all. It's up for discussion. You can ask your neighbor. Anyone thinks they have a good idea? Random idea? Crazy idea? Oh.
Does the second row, second person, is she like someone who studies anatomy?
An anatomist? Not entirely sure where you're pointing, but yes, but not quite what I'm looking for. This is not a list of anatomists. Any other guess? Right, these are all the women who won the Nobel Prize. Here's their names. Nobel Prize for Physiology and Medicine. It's 13, and we had to update them this year when she won the Nobel Prize as well. Now, I asked my student to put them all together and show me the face of the female Nobel laureate. What do you need to look like as a woman to win the Nobel Prize? Here you go. That's what you need to look like to get the Nobel. Now, there's a couple of problems that you can see here. And one is that this face, even though recognizable and has some similarities with some of the women around it, it doesn't actually match them 100%. The other thing is that some of the features, like the leopard print here, which comes from France, are clearly visible, but other features seem to be lost in the average image. Now, the point that I'm making here is that when you average our faces, you will get a face that looks like a human face, but it won't match the individual faces that you use to build it. And this is plain obvious when we do it with faces. It's a lot less obvious when we do that with the brain. And in neuroimaging, this is what we do all the time. We take all the brains and then we just average them to make them all look the same so we can work with them a lot easier in softwares. Now, this is the average brain, and areas where the template is very sharp means there is less variability, and areas where it's blurry, like here, means there is more variability. So confronted with variability between us, the template ends up being a bit blurry, meaning it's a little bit unsure about the exact anatomy here. Now, if we look at two examples of how different the anatomy can be, I used a cross-sectional approach here for the motor cortex, and you can see that classically the textbook tells you that the hand knob area, so the part of the motor cortex that's in charge of your hand, looks like an inverted omega sign. But in fact, what you can have is either an inverted omega or an epsilon or even a straight line or anything in between those configurations. Now that's for the gray matter. For the white matter, I have an example here drawn from two healthy participants. And if we just look at the uncinate fasciculus, the hook between the frontal and the temporal lobe, it's barely visible for this healthy participant. And when we compare it to this one, it's extremely prominent. So this is the degree of variability that we're dealing with in the brain. Yes?
Does it still indicate
That is a very good question, and you're about 5 slides ahead. But the very short answer is yes, it does. Now, what I'm showing you here is just hand-picked examples. So obviously we wanted to look at this in a proper and coherent way and actually map the variability in the grey and the white matter at the group level. And what you can see here is the variability on the surface of the brain, so the cortical areas, grey matter, and the white matter, the connections of the brain. And what you can see in both these maps is that there is a gradient. And that gradient means it's blue on the inside and warmer colors on the outside. And blue here, the colder colors mean more alike, so more similar. And the hotter colors mean more variable between individual brains. Okay, so what you see is a gradient whereby the deeper and older parts of the brain tend to be more alike between us. And as you go more towards the surface of the brain, you see hotspots of variability across the brain. Now, that's interesting in its own right, but this is also very relevant when we come back to neuroimaging, because we tend to use template brain, average brains, which works okay-ish as long as we're working in a healthy brain. But the second you bring this to a patient, it doesn't work anymore. And I have one example for you here. So in green you see a tumor lesion, and in blue you see the reconstruction using diffusion weighted imaging for the corticospinal tract. And when you zoom in, the red outline here is where an atlas predicted that the corticospinal tract should be. Now, if any neurosurgeon would operate based on atlas, they would completely miss the actual tract. So it's always important to look at the individual anatomy, especially in clinical populations. Yes?
Is there a reason why the inner part of the brain has less variability than the surface?
Yep. There's a couple of reasons. One is the evolution of the brain. So you have the dual origin theory that postulates how the brain evolved and develops. From certain structures, it kind of turns outside. So that's one of the reasons, because those parts inside the brain tend to be older and first developed. The other reason is that we're exposed to experiences, and the brain is inherently plastic and adapts to our experiences. And the outer parts of the brain are the neocortex that are more influenced by learning to read or learning to drive a car, things like that. Yeah? Now, coming back to your question, does it matter? That is the question. And this is a project that we started in the early days of COVID and thought it would be a quick and fun project to do. Turns out it took us a year, and at some point it wasn't as much fun anymore as we thought initially. But we did learn a lot. So what we did is we looked at the anatomy, looking at the variability in white matter and the variability in cognitive performance. And it turns out, quite to our surprise, that there's 326 studies that actually did that. We thought there was a bit less than that. And looking at them, a couple of things we learned. So the first thing, again, quite to our surprise, that we learned was that most of what we know about the function of the white matter, we actually know from clinical cohorts, not from the healthy brain. So 45% of the studies were conducted in neurological and neurosurgical patients, 29 in psychiatric patients, and only 25% in healthy participants. The other thing that we learned is that some tracts are superstars in the field, like the corticospinal tract, whereas others, like the accumbofrontal pathway, are largely ignored. And it depends on the field. So the corticospinal tract is obviously extremely prominent in neurology and neurosurgery, but a lot less so in psychiatry and healthy controls, for example. Yes?
What did they do with the healthy participants to like discover how the white matter works?
Right, so in patients you obviously have the deficits, and in healthy controls you can just do performance tasks, behavioral measures, cognitive measures, and correlate those indices. And this is what they did. So this is inherently difficult to read, so we're just going to zoom into the arcuate fasciculus. That is classically considered the language pathway. But actually, when you look at the literature, it correlates with sleep, memory, language, executive functions, auditory functions, attention, and motor functions. And this is a pattern that we found for every single one of the connections that we looked at. So the point here is that there is no one tract, one function association, but that a tract can tap into various cognitive domains depending on the situation that you're in. And I think this might be a good time for a quick break. Any questions? So summary for the part that wasn't recorded. Conduction aphasia, not the long segment, but the indirect segments of the arcuate fasciculus and the inferior parietal lobe. And language is very dynamic by activating various different parts in the left and the right hemisphere when you name an object like a pencil. Right, that brings us to this. So, language initially was described in a modular approach to the brain, meaning one part of the brain, one area does one specific function. And you call that either modular or localizationism, but the idea is the same. One area has one function. Now we have seen that that is very likely not the case, and it's quite a limited model. Moving on to the hierarchical model where things are connected, but they're connected in a order. So if we think about the conduction aphasia patient again, then for repetition you first have to hear and comprehend and then send the information forward to articulate. So that's a hierarchical model. And that can be direct or indirect. But then the video that I've just shown you looks more like the integrative model, where you have different parts that come activated and deactivated across time depending on their need. And when we look at the computational power behind those models, when you have three areas, X, Y, Z, and the different states being active or non-active, there's pretty much only three activation states you can have, because the part of the brain is either on or off, right? Given how complex and dynamic language is, this is probably not enough to have those very complicated linguistic computations that we can do. So unlikely that this model actually works. Now, if we connect those three areas, they can either be all on, so active, 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 or if you choose the direct route, then active, inactive, active. So this would be here, active, inactive, active. Again, very limited range of possibilities for processing power. When you move to an integrative model, whereby the sum is more than the individual parts of the areas, suddenly the computational power of your model increases dramatically, and we're getting closer to potentially explaining how language works in the brain. And that's just by changing the assumption how we think the brain works. Right, so move, yes?
More in creatures with more limited intelligence, would the first and second model be more likely?
This is not really dependent on intelligence. This is more the individual processing steps that you need for a given function in the brain. So this can be language or other functions. We just exemplified it with language, but it's more a model of how the brain works rather than dependent on IQ. Yes?
How is it in animals? Because they don't have language as we know it.
I don't know. I went to a conference very recently where they apparently described the arcuate fasciculus in the chimpanzee. And my question to them was pretty much your question to me. I'm like, okay, if the chimp actually has an arcuate fasciculus, what does that mean? Because then technically the arcuate shouldn't be a language pathway, because chimps, by our definition of language, don't really talk. We didn't get there yet, I don't know. But we're gonna find out once the findings are validated and we know it's not just an artifact.
We know that chimps communicate, right? But what is the difference then with communication and speaking language?
That definition depends on who you ask.
In terms of neural networks, is there a difference between language speaking and communication?
Yes. So communication usually requires additional channels, so gestures, for example, facial expressions, those kind of things. In terms of the difference in the brain, up until now, the arcuate was not there in non-human primates. That would be, people looked at chimps and macaques. Couldn't find it until now. This is the first time it was described in a chimp brain. But also for the ventral network, the IFOF for many years, for example, was described to be unique to the human brain and not there in the non-human primates. But it was actually described by someone from the Dondas who found it in the monkeys. So, the anatomy keeps evolving. But in terms of the difference between language and speech, yes, non-human primates do communicate, but they don't have a linguistically complex language like we do. Any other questions? Yes?
To find a brain track that they didn't know before that like a chip had, did they like do something differently? Because what did they do?
They did a couple of things differently, but the main difference is that they used a different scanner and a higher resolution of the scanner. Now the problem here is that they used a high resolution scan and then they thought they validated it by looking at the maps that you get from the scan and by doing tractography. The problem is the map and the reconstruction of the track go back to the same scan. They come from the same signal originally. So that's not a validation. You're just showing the same thing twice using effectively the same data. So what we suggested they do is either scan a human brain using the same scanner, so at least you have some comparability to what we know about the anatomy in the human brain and can then make inferences about the quality of the scan, or do postmortem dissections in the chip, which is what we're going to do.
Cool.
And then we know if it's there or not. Any other question? No. Okay. Now, what do we do with all of this? So, coming back to AI, if you put in search terms like machine learning, brain and predictions, you get pages and pages of discoveries where people apply AI to predict what the brain does. And obviously we want to do the same. We want to know when a patient comes in and has a stroke or a brain tumor, how that patient will be in a year down the line. Now, in order to do that, we come up with an overall model, and I'm borrowing examples here from something that, again, is a lot more tangible than what we do in the brain. And that's climate change. Everyone knows about climate change. So you create a model based on all the data that you have. You throw all the data into the model and you make predictions. Right now we're in the sweet spot, as everyone knows, and we can make a choice to make dramatic changes, and apparently the future will look cooler, or not make dramatic changes and everything is going to get very hot. Now, one of the first things that you then want to do is to check, well, what does that mean for me? So you get a map of Europe, you check where you are, and then I think we're about roughly 1 degree in the Netherlands. And then based on that, you make your changes, and we're supposed to take public transport a bit more. And if you rely on Deutsche Bahn, you stay home a lot more. And that's pretty much what we do in the brain. We make our models, we come up with personalized predictions, and then ideally we tailor therapeutic interventions based on the personalized predictions. Now, while everyone is somewhat familiar with these models, brain models look like this. So it's a lot less intuitive. Now, let's go through it. So you have a patient. The patient has a lesion here, or here, or here. What we do with that lesion, we put it onto the atlas and get the patterns of the disconnection. So all the white matter that is affected by the lesion, all the brain connections that are relevant or disconnected in that case. And then we make a map of all the patients, and we've done this for 1,333 patients to get quite a comprehensive map of which disconnections of the white matter you can get depending on what kind of lesion in the brain. Now, based on this map, we can then take an individual patient, a new patient, and compare the new patient to the map that we have. Now, for these patients, the 1,333 patients, we know their outcome. So we know the lesion, we know what the lesion disconnected, and we know how they were at 3 months and 1 year. So if we now throw in a new patient, based on the anatomy of the lesion, we can predict that that patient, for example, lands here, which is the occipital right white matter, apparently. And based on that, we can come up with a personalized prediction of where the patient will be in a year's time, given the sample data that we had from the over 1,000 patients. And this is one such example where you can see the lesion right here. And then in red, you have what the model predicted, and in blue, you have what was actually measured for that particular patient. And it's pretty good match for measures of visual spatial memory, verbal memory, pain, sickness, motor functions, language, and visual spatial abilities. Now, the model has about 87 neuropsychological measurements and behaviors that it can predict, and it's available as a website called the Disconnectum Symptom Discoverer. So anyone can use it. It's open science, freely available. Anyone can use the model and apply to their own data, which is something that was recently done by a group with Tom Hope and Kathy Price at UCL London. They saw the model, they wanted to try it on their PLORAS data. The PLORAS is the predicting language outcome in recovery after stroke. It's a huge database. They collected for over a decade. And what they did is they used their patients, their lesions, and put it into the model to see how the model predicts the outcome of their patients. And this is data the model has never ever seen before. It was completely blind to it. And they tested it for naming and for fluency, and the model worked. Within a margin of error, obviously, so you never get 100%. But the model actually made quite a good prediction of the outcome. Should say it's not submitted anymore, it's now published in Brain. So this is how we can use the data from individual lesions, put it into the model, inform the model based on the large data sets that we have, and make predictions for the future. Now, if we bring this all together, then if you ask where language is in the brain, it's a bit like asking where a piece of music is. It's not in the conductor, it's not in the individual notes, it's not in the individual musician. It's the entire orchestra coming together in a coherent, effective way over time that lets the music emerge. And the way we think about language in the brain is very similar to that, whereby you have those different areas in the brain that are important for language. So you have certain hubs for semantics or syntax, but only when you put it all together in a coherent way and look at the dynamic changes in the interaction over time is when language emerges. So the modular way of looking at the brain is probably oversimplifying it, and we believe that is more the interactive model that can explain how language works. Yes?
I've got a question about the model.
Yes.
Is the model only in regard to the language? Because I'm thinking about all the factors that could contribute in the model, but I believe it is still remarkable that the model actually works. So what are the actual factors involved in language in the brain?
That's a very good question. You can dissect language into multiple individual processes, right? So language is obviously speech output, it's linguistic structures, it's semantics, it's syntax, it's concepts, but it's also memory. You can't really talk without using verbal working memory. Tapping into concepts also means you have to have a memory of what a concept is or what a thing is. And you need executive functions, top-down modulation. So it's you can't separate language from those other cognitive domains, which is also why in the model we have 87 neuropsychological assessments tapping into visual, spatial abilities, working memory, and so on and so forth, to have a full range of predictive power.
But also age and sex and medical history.
Medical history we didn't have in this sample, but the assumption would be that the more you know and the more you can add to the model, the better the prediction should be in the end. But it's surprisingly hard to get data sets that actually have all this information. And you need a lot of data, that's the other thing. To train a model and then have an out-of-sample test, you need a lot of data. And even for the healthy brain, we don't have that much data. Like one of the biggest data sets that we have is the Human Connectome project. That's 1,200 something people. It's not that many. Like it's great. It took years to collect the data, but it's not that many people. It's even harder when you do that with patients, because that data is harder to obtain in the first place, but also ethically and the European guidelines with GDPR, it's not easy to share the data. So while there is open data sets for the healthy brain, where you can literally just go online and download the brains of 1,200 people and look at it, you can't do the same for patients. So all this work is then based on collaborations, willingness to share, and possibility to share. And oftentimes that is limiting what kind of data you can share. So sharing lesions is easy. It's a mask. It looks, if we go back, it looks like this. So what someone would share is just this black spot here and here and here. That's fine. You can't reconstruct the face from that, which you can from a T1 scan. that data is fine to share. The second you attach demographics, clinical history, other factors, you start being able to potentially identify that person, and that's why the data is segregated. So the clinical history we didn't have, long story short. But we're working on building international consortia to actually try and facilitate the flow of clinical data, which is working in parts, but not to the extent that it would be needed at some point, just yet.
Thank you.
Mm-hmm.
This models for language, is there a possibility that models like this are also created for other functions?
Yes. So that particular model, obviously I'm totally biased and I'm interested in the language part, but you can also use that model to predict motor functions or memory or visual spatial abilities. So I just zoomed in on the language assessments. But it's 87 neuropsychological tests, so you pick and choose the ones that you're interested in the end. That is all I had for you. Thank you very much. And if you want to join us for NeuroNijmegen every Monday morning, you're welcome.